Okay, so welcome to the first lecture on the vectors course. This is the basics, vectors versus scalars, vector notation, addition and scaling, and properties. Alright, so begin at the beginning. Let's list some scalar quantities. Think about mass, duration, length, temperature, charge. These physical quantities are all well described with a single number. Really, they just have a magnitude, although some of them may go negative, so it's a magnitude and a sign. But still, just a simple number is adequate to describe these things. How about vector quantities? What's different about vector quantities? Well, think about these things: force, velocity, and therefore acceleration, or momentum. These things also have a strength or a magnitude. However, so let's put that down. They have a magnitude. However, they also have a direction. More than just a sign, they have a full-on direction in three-dimensional space. So it's not enough to know that a force is 3 newtons. I want to know in which direction is that force applied. And that then is the difference between a vector and a scalar quantity. We're going to think about how we manipulate them. Alright, so first off, the notation that we're going to use when we talk about our vectors. What I'm going to do is I'm going to use a symbol such as the letter A. So let's write that out, but I'm going to underline it. So an underlined symbol indicates a vector rather than a simple number. And when I need to specify that vector, I'm going to write it, so it's going to be three-dimensional. I'm going to write the three numbers in a column form like this. Now, if you haven't seen a vector specified before, what does it mean? Well, think of the Cartesian axes, the x, y, z axes. Think in this case about coming out from the origin 2 in the direction of x and 1 in the direction of y and 3 in the direction of z. What we're going to do is we're going to think of our vector as an arrow that comes from the origin to this point in space. And that arrow itself, whether or not it comes from the origin, that direction and that length of arrow is our visualization of the vector. So let me just change color to green and go ahead and draw the tip of my arrow there. There we are. So the vector is coming towards us out of the screen, and it has those particular three components, 2, 1, 3. Other people may use other notations. For example, a line over the symbol A is commonly used. When people write out the components, they may choose to do it as a row like this, or even using pointy brackets like this. Now, all these notations are basically getting at the same thing. You'll be able to read textbooks or look online and see these things and understand what they mean. But within this course of videos, we're just going to use the notation that I've introduced above, so I'll erase those for now. Now, the simplest thing that you might want to do if you have a couple of vectors is to add them up. So let's think about that. Vector addition, what does it mean? So let's give ourselves a second vector b. We'll make it 5 minus 2, 0, let's say. I want to add these two vectors together. So we'll write that out. I simply want to add a underline plus b underline. What does that mean? Let's just substitute in 2, 3. Add it on to 5 minus 2, 0. Now what we do is we simply add the first component of vector A to the first component of vector B, and so on down the list. Very, very simple. So we're adding 2 plus 5. We're going to add 1 plus minus 2 and 3 plus 0. And we just tidy that up. So that's going to be 7 minus 1 and 3. Now, how about scaling a vector? Okay, so what we can do is we can multiply a vector by a simple number, and correspondingly we'll just end up multiplying each of its components. So let's take an example: 3, 9 minus 12. What we notice is each of the three components is a multiple of 3. We can just take that common factor out in front and write this instead as 3 times 1, 3 minus 4. Same thing. Alright, or equivalently, someone might give us a vector that's already written in this form. Could be, let's say, 3 over 2 onto 2, 4, minus 4, let's make it 1. All right, and we can just multiply that in a component by component basis. So we just write ourselves a new column. Of course, 3 times 2 is 3. 3 times minus 4 is minus 6. And 3 over 2 times 1 is 3 over 2. Okay, so there we are. We can scale our vectors by a number in this simple way. So with these definitions of addition and scaling, can we say anything about the properties? Okay, so if I have two regular numbers a and b, then of course a plus b is the same as b plus a. I'm not saying anything fancy here. It's as simple as, I don't know, 7 plus minus 3 is equal to minus 3 plus 7. Obviously it is, we know that. Now, if we think about the same statement for vectors, a plus b, vector b, is it the same as vector b plus a? Well, it must be. Let's just write out an example. 7, 0, minus 1, 3, 1, 2. Is it equal to 3, 1, 2 vector plus the vector 7, 0, come on, 7, 0, minus 1? Of course it is, because of the way we've defined vector addition as just being the addition of each element to the corresponding element. And this property is called being commutative. Okay, so vector addition is commutative. How about this second example? If we have three basic quantities, ordinary numbers, then if we have a plus b plus c, it's the same as a plus b plus c. It doesn't matter the order that we do them in. Is that going to be true for vectors? Well, of course, it is going to have to be true to vectors, because the way we define vector addition is to add each component to the corresponding component. It's just addition. So this is also for vectors. And let's write out what we mean. We mean that vector a plus b plus c as a previously worked out thing is equal to vector a plus vector b and then add on c. It doesn't matter the order we do these things. Alright, and there's a name for that property. It's called being associative. Alright, so vector addition has that property also. Now let's think about our scaling property. If we have ordinary numbers again, then we could take some scale factor k and multiply it into a plus b, and it would just give us k times a plus k times b. Again, I'm not saying anything that isn't utterly obvious here. Say, for example, I don't know, 2 into 1 plus minus 3 is equal to 2 times 1 plus 2 times minus 3. Of course it is. So how about for vectors? Is it true that some scale factor k times the sum vector a plus vector b, a plus b, and let's stress that this scale factor is just a pure number? Then, yes indeed, it's going to be just k times a plus k times b. So just to stress what we're doing here, let's copy down this sum of two vectors we were playing with up here, this 7, 0, minus 1 thing, plus 3, 1, 2, put it inside curly brackets maybe for a variety, doesn't have to be curly brackets, multiply it by some factor. Let's have 3 over 2, had that before, unimaginative, there we are. What's that going to be? It's just going to be 3 over 2 times the first vector, 7, 0, 1, and then plus 3 over 2 times the second vector, 3, 1, 2. Okay, so everything as you kind of would expect it works out. It must. And this latter property is called being distributive, excuse me. So scaling is distributive over addition. And that's the end of our first video. Welcome to the second of these videos. We're going to look here at the vector dot product, also called the scalar product. We'll look at also the magnitude of a vector and the meaning of unit vectors, the geometric meaning of the dot product, and finding the angle between vectors using the dot product. Okay, so the dot product is a way of combining two vectors in order to produce a number, a simple number, a scalar, hence the alternate name scalar product. Let's give ourselves a couple of vectors. Let's have a, well, vector a can be 4, minus 4, let's have 2, 1. And we'll have a vector b, which can be 3, 1, 3. And we're going to do the dot product of these two guys. So we write that as vector a nice clear central dot, vector b, and then we write that out as the two column vectors, and we need to understand how we compute the dot product. And the answer is we're simply going to multiply each component by its opposite number and then add them up. So we're going to multiply the first component, minus 4, by 3, and then add that to the second component 2 multiplied by its opposite number 1, and finally the third components 1 and 3. So that's minus 4 times by 3 added on to 2 times by 1 added on to 1 times by 3. So minus 12 plus 2 plus 3, that's going to be minus 7. Alright, there's the dot product worked out. Pretty straightforward. And of course, as you can see, it can be a minus number. It can be 0. It can be a positive number. But it's a simple, pure number. Okay, so now let's see what happens if we do the dot product of a vector with itself. Let's do A dotted with itself. So that's going to be minus 4, 2, 1 dotted with minus 4, 2, 1. Now, of course, because we're multiplying each component by itself, that will always be a positive number. 16, minus 4 by minus 4, and 2 2s are 4, and 1 1 is 1. And so that's going to add up to 21. It must add up to a positive number. It's made of 3 positive numbers summed. Now, I want to introduce a second vector called A hat. It's related to A just by scaling it. And we're going to scale it by 1 over the square root of the earlier dot product with itself. So 1 over square root 21. And then just minus 4, 2, 1 as before. So that's just a scaled version of A. What's interesting about it? Well, now let's see what happens if we take the dot product of A hat with A hat, with itself. So we're going to get 1 over square root of 21 times 1 over square root of 21, which is 1 over 21. And then, of course, we're going to get A dotted with A, the original dot product we did, which is just 21, as we know. So, of course, the dot product of A hat with itself is just 1. That means that A hat has a special property. It's what's called a unit vector. Unity being, of course, a fancy word for the number 1. So when we scale a vector so that when dotted with itself it comes out as 1, then it is a unit vector. Meanwhile, in general for a vector, the square root of the dot product with itself has the name magnitude. This is the magnitude of a vector, and it is also magnitude. It is also the length of the arrow if we think in terms of a vector as a physical displacement, an arrow that lives in 3-dimensional space. Then it would be the length of that arrow, as you can see from Pythagoras. Okay, now then, a different thing. The dot product between two vectors has an alternative definition, which we can show is the same as the definition we've been using so far. A dot B is also the magnitude of A times the magnitude of B times cos of some angle. And what is that angle? It's actually just the angle between the two vectors, between their directions. So here I'm drawing a vector A going in one direction and almost in the opposite direction vector B. And then the angle in question would be this angle that we see between the two vectors when we draw them coming from a common point of origin. Okay, so it's important to understand then that this angle can be more than 90 degrees. Here's what it isn't. Here's a mistake that's sometimes made by people as they start to play with vectors. They want the angle, for some reason they want it to be less than 90 degrees, so they try and contrive this by putting the vectors together in a way that will give them less than 90 degrees. Like this, for example, and then we could try and draw an angle between these two lines. Let's see, let's use a red to show that it's not correct. What we should have is the two vectors coming from a common origin. Then we see that the angle between them can be more or less than 90 degrees. If it was exactly 90 degrees, then of course the dot product would be 0, because cos of 90 is 0. That has interesting consequences. But right now let's work out the angle between a couple of vectors. Let's give ourselves A, we'll make it 1, 0, minus 1, and B, we're going to make it 4, 1, minus 1. And we'll do the dot product between those guys. So first we'll work out the dot product. Actually, let's make it minus 1. So A can be minus 1, 0, minus 1. I think that will come out better. So we have minus 4 from minus 1 times 4. We have 0 times 1 is 0. And we have minus 1 times minus 1 is 1. So it's going to be minus 3 for the total dot product between these two guys. But we also need to find out the magnitude. Fair enough. The magnitude of A is going to be the square root of minus 1 times minus 1 is 1. And again, 1. So that would be the square root of 2. Nice and straightforward. Meanwhile, the magnitude of B is going to be 4 4s are 16 plus 1 plus 1. It's going to be 18, the square root of 18. but I think we can do better than that. Square root of 18 is actually square root of 9 times the square root of 2, and that means it's 3 times the square root of 2. Okay, now we've got everything we need. Let's pull down a copy of that definition there, relating a dot b to its magnitudes and the angle, and fill in what we know for this particular choice of a and b. We've got minus 3 is therefore equal to root 2 times 3 root 2 times cos of the angle that we're after. So now we just need to rearrange. That means that cos of the angle is going to be equal to minus 3 divided by, well, we've got two lots of root 2, so that's just going to be 3 times 2, and if we simplify that down, it's just going to be minus a half. Now we may just remember, or else use a calculator to find out. This means that the angle in question is in fact going to be simply 120 degrees, or you can use radians if you prefer radians. So there we are, that's the answer. The angle between these two vectors, 120 degrees. And that's it for the second video. In this video we're going to see how to calculate something called the cross product of two vectors. It's also called the vector product because the output is a new vector, and we'll see how to test that the answer is correct. So here I've written A cross B is equal to C, and notice that the symbol for the cross product is just the multiplication symbol that you're familiar with from basic arithmetic. I've given the vector A a particular form, this 2, 3, 4 column vector, and similarly B is written as 4, 5, 6. So we're going to go ahead and find out what is the cross product of these two vectors C. Because it's a vector, we'll need to do some working for each of the three components. Now what I'm going to do is I'm going to paste up some structure to help us work through the problem. So don't worry, because it's going to look like a lot, but you don't need to write all this out every time you want to do a cross product. I'm just putting it here so we can really spell out the process. Okay, so let's go ahead and work out the first component of the output vector C. Strangely enough, what we're going to do is we're going to ignore the first component of vectors A and B. So I'm just going to cross those out. Those aren't used. And what we're going to do is we're going to multiply certain of the other components. What we're going to do is we're going to multiply the second component of vector A with the third component of vector B. I call that the falling diagonal, because when we draw it like this, we start high and then go low. And then we're going to subtract off the multiple of the rising diagonal, 4 and 6 here, the last component of vector A and the middle component of vector B. So what we have here is 21, that's 7 3s are 21, minus 6 4s are 24, that's minus 3. And we can go ahead now and write that in as our first element, minus 3. Now let's move to the second element of the output vector C. We'll start by ignoring the second component of the two source vectors A and B. We can cross those off. And again, we're going to multiply some diagonals. But what's different here is we start with the rising diagonal, 4 times 5. The last component of vector A times the first component of vector B, the rising diagonal. 5 4s are 20. And then we subtract off the falling diagonal, so 2 7s are 14, and that's going to give us 6. So we can put that in. Now let's move to the third and final component. As before, we start by noting that we will ignore the third component of the two source vectors, and we're going to need some diagonals. It's the same pattern as the first, falling diagonal first, so 2 times 6, and subtract, which is 12, and then subtract off the rising diagonal, 5 3s are 15. Alright, so that's going to be minus 3. Pop that in. We see that we have quite a simple vector here. There's a common factor of 3. Let's bring that out. 3, then minus 1, 2, minus 1. That is our vector C. That is A cross B. Notice again the pattern. It was the falling diagonal minus the rising diagonal for the first component, and then the rising diagonal minus the falling diagonal for the second component, and then for the third it was back to the same pattern as for the first. Now these look a bit like letters to me. They look a bit like a V, the middle one perhaps an N, and the final one a V. I like to remember that as a little sentence, which is vols never vary. Because in my opinion, vols don't vary very much. Here's a vol. This one doesn't vary at all because it's stuffed in a museum. However, if you compare it to some other vols, which I found these on the internet, I think they are all pretty much identical. I don't see a big difference there. So for me, vols never vary. If for you, they do seem to vary, then think of a different way of remembering it. But the important thing is that the first thing is the falling diagonal, and then subtract the rising diagonal, a V shape, and it alternates. Okay, how to check your cross product has been worked out correctly. This is really useful stuff. So let's give ourselves another example. We'll have 2, 3, 1, and then we'll have, let's say, 3, 7, minus 1. Let's get a minus in there. And that's going to be equal to something. We'll work it out in a minute. For now, I'll put x, y, z. Now, how am I going to test, once I've found those x, y, and z, that I haven't made some kind of slip? I mean, there's a lot of mental arithmetic. If we don't write it all out, we're going to be doing a bunch of multiplications. I could easily slip up. How am I going to test that? It turns out there's a very interesting property of the vector c that we get out after the operation if we've done it correctly. That is, as I've written here, that a dot product with vector c is 0, and so is b. So either of the input vectors a and b dotted with the correct cross product c should give us 0. And that's great because the dot product is very easy to work out even by eye as a check. Let's go ahead and do it. So I've copied it down here. We're going to want to work down our various components. Let's do the first component of c. So what do? We ignore the first components of a and b, and we do the falling diagonal. So that's going to be 3 times minus 1, and we subtract the rising diagonal, 1 times 7. So actually, let's just write that out. Normally, I wouldn't bother to write all this out, but let's go ahead and do it here. So it's minus 3 minus 7, and so that's going to be minus 10 as our first component. Now we work out the second component. We ignore the second component on the input vectors. We do the rising diagonal, 1 times 3, and subtract the falling diagonal, 2 times minus 1. So what have we got? We've got 3 here minus 2, and so that's going to give us 5. And then finally, the third component, ignore the third component of the input vectors, do the falling diagonal, 2 times 7, 7 2s are 14, subtract the rising diagonal, 3 3s are 9. So we're going to have, for our final component, 14 minus 9, which is another 5. Aha! So that's quite a simple vector, has a common factor of 5 in there, if we wanted to write it out that way. Now let's test that guy versus the a and b vectors to see if it passes our test, or have we made a slip. So let's just be completely explicit about that. We're going to start by testing the dot product of the vector a with our hopefully correct cross product c. I'll write it out, 2, 3, 1, dot product, minus 10, 5, 5. What's that going to be equal to? Minus 20, and then 3 5s are 15, and then 1 5 is 5. Aha! It does equal 0. That's correct. That's a very, very encouraging thing, but for real thoroughness, we're going to test the other one as well. So this is b dot c. Let's check that out. So that's 3, 7, minus 1, dotted with, again, minus 10, 5, 5. This time it's going to be minus 30 from 3 times minus 10, and then 7 5s are 35, but then minus 5 from the last element, 0 again. Aha! So it has, in fact, passed both of our tests, and we're now very confident that's correct. This is a great test to do. One word of warning, though, the one thing it won't pick up is if you've done your rising and falling diagonals in exactly the wrong way round by starting with the wrong pattern. So do remember the VNV pattern, and this test will check for any particular slips in your multiplications. And that's the end of the video. Okay, so in this short video, I'm just going to look at 4 more examples of the cross product for practice, and here they are. Okay, so here's the first one. We want the first element of this cross product, so we ignore the first elements of the two source vectors. We do the falling diagonal, 3 times 0, that's 0, and we subtract the rising diagonal, 7 times minus 1, that is minus 7. So we're subtracting minus 7, that means we'll get plus 7. So the first element here is going to be a 7. Okay, so now we want the second element. That means we ignore the second element of the two source vectors. We do, however, the rising diagonal first. 7 2 is 14, minus 1 times 0 is 0. So that's 14. So the second one was the rising diagonal first, if you follow me. And then finally, to get the third component, we ignore the third component of the source vectors, and we do the falling diagonal. 1 times minus 1 is minus 1, minus 3 2s are 6. So that is minus 7. Okay, so there's our solution, 7, 14, minus 7. But is that correct, or have we made a slip? it's a good time to check the old dot product trick. So if we call this A cross B equals C, then we should find that if we do the dot product of one of the input vectors, say B, with C, then it should be 0. Let's check that. 7 2s are 14, minus 1 times 14 is minus 14, 0 times minus 7 is 0, so that's 14 minus 14. It's correct. Let's do the other one. It's harder. So 1 times 7 is 7, 3 times 14 is 42, so that's 49 in total, and then the final term here, 7 7s are 49, but that was with a minus number, so we've got, in fact, 49 minus 49 is 0, so another one of those dot products is correctly 0. So what we found out is that A dot C and B dot C are both equal to 0, as they must be, so we're now very confident that we have the right cross product there. Let's do another one. Okay, so we're going to want the first element, so we ignore the first element of the two source vectors, and we do 8 3s are 24 minus 2 times 1 is 2, so that's 22. Let's do the next elements. So we ignore the middle elements and we do the rising diagonal. 4 2s are 8 minus 8, that's just going to be 0. And then finally we ignore the bottom elements and we do the falling diagonal minus the rising diagonal. 1 minus 12 is minus 11. So there's our solution, 22, 0 minus 11. We notice we could take 11 out of that as a common factor. That would make the next stage very easy, but let's just let's do it the hard way and do the dot product. So 4 times 22 is 88, 1 times 0 is 0, and minus 88. Actually pretty easy to confirm that's 0. Let's do the other one. 1 times 22 is 22, 3 times 0, and again 2 times minus 11, again 0. So that's fine. That one's passed its checks as well. On to the third one. Okay, so this time I think I might take a common factor out just to show us doing that, because I see that this 25, 5, 15 chap is going to lead to some pretty big numbers. But maybe I don't need to do that. I can just take the common factor of 5 out of the first vector. We're calling it vector A. So that's just 5, 1, minus 3. And then I go ahead and write vector B, which can't be simplified as just 1, 3, minus 2. We'll do this cross product, and then we'll put the factor of 5 in at the end. That's fine to do it that way round. Okay, so let's go ahead and write that out. There's our factor of 5, and here's our cross product. So the first element of our cross product, we ignore the first elements of the two source vectors. We do the falling diagonal, that gives us a minus 2. We subtract the rising diagonal, that's a minus 9. So that's minus 2 plus 9, that's going to give us a 7. And now the middle element, we ignore the middle elements on the two source vectors. We do the rising diagonal this time, gives us minus 3. We subtract the falling diagonal, that gives us minus 10, which means we're going to have to add on 10. So that's minus 3 plus 10, it's another 7. Okay, and then finally, the third element, we ignore the third elements on the source vector. We do the falling diagonal, that's 5 3s are 15, and we subtract the rising diagonal 1. That's going to give us another 14. So in fact a really simple vector here, because we could take out a factor of 7 if we want to, but let's check those dot products. Do it before or after we take out the factor of 7. It's pretty easy. That's going to be 4 times 7 minus and minus 2 times 14. Yes, that goes to 0. Let's do this one just quickly. 35 and another 7 is 42, but minus 3 times 14 is exactly minus 42, so that one is also satisfied. We've passed our checks. That looks pretty good. We can leave it like this, or if we want, we can take out that factor of 7 and do 35 times 1, 1, 2. Very simple, very nice vector there. Okay, let's come here now, come down to the bottom and look at the final one. We notice it's actually the cross product of a vector with itself. It's the same vector here. So what are we going to get? Well, we can just easily enough work it out. We ignore the first two elements and we do 2 times minus 4 and minus 4 times 2. So it's something minus itself. That's just going to give us a 0, obviously. And let's keep going. If we ignore the middle terms and do the rising diagonal minus the falling diagonal, again, 3s and minus 4s, the same product. So something minus itself, 0, and it's going to be the same for the final element. So the cross product of a vector with itself is always going to be the 0 vector. Now, it's important not to write that just as the scalar 0, Because it is a different object. It's the vector 0. It's a set of, in three-dimensional space, 3 zeros. So that's what we get when we cross a vector with itself. Of course, this is going to trivially satisfy our condition on the a.c is equal to 0 and b.c is equal to 0. That's clear. And so I think that's a nice set of 4 examples done quite quickly there. They're not too bad, are they? So that's the end of the video. Okay, in this video we're going to look again at the cross product, but this time we're going to ask about its geometric meaning and its properties when we come to manipulate it. Okay, so if some vector c is the cross product of two other vectors a and b, we've already seen how to work that out. But what we can reasonably now ask is, what does that vector c look like? You know, if we imagine a particular couple of vectors a and b there in space, where is this vector c? How is it related to them? We know how to work it out, but what's its relationship with them? How should we think about it? And that's what we're gonna figure out now. So we know that c is a vector, so it has two properties. It has its magnitude and direction. Let's think about the magnitude first. What is the magnitude of c, and how does that relate to a and b? What is the length of that vector? It's pretty simple. The magnitude of c is the magnitude of a times the magnitude of b times sine of the angle between a and b. This is very similar to the dot product, except with a sine instead of a cos. So there we are. There's our two vectors a and b and an angle between them. And from those magnitudes, the lengths of those two vectors and the angle, we can work out the magnitude of c. Note that if we cross a vector with itself, the angle will be 0, and so the cross product will be 0, just as we've already seen in our examples. That was easy enough. What about the direction of this new vector c? How does that relate? Okay, here's the thing. The direction of c is perpendicular, sorry for my writing there, wiggly writing, c is perpendicular to both vectors a and b. So it's at right angles to each of those vectors separately and simultaneously. What does that look like? Well, actually, we can draw it in one of two ways, one of which is right and one is wrong. Let's just do that. So here's our vector a, here's our vector b. If we draw c like that and make it clear with this little symbol that it's at right angles to those two vectors, that would be perpendicular to them both. How about this? We could also draw vector a, draw vector b again, and we could go in the opposite direction, simply literally the opposite direction, and that would also be perpendicular to these two vectors. One of these is actually strictly the correct case, and the other is wrong by essentially a minus 1 multiple. What's the way to work that out? So let's now figure that out. There's actually a rule to remember it by. It's called the right-hand screw rule. So let's draw that out kind of really clearly one more time. We have two vectors a and b, and we are going to say that a cross b is equal to some vector c. That's fine. So what we do is we put on the line along which we know c must lie. So this is the line that's perpendicular to both a and b. And we simply have to ask ourselves, in this picture, does the vector c go upwards or does it go downwards? The trick is to write on the angle between a and b and give it a direction so that it's increasing from a to b. It's the angle from a to b. Then you imagine taking your right hand and gripping that line in such a way that your fingers curl in the same direction as the angle increases, and then your thumb points in the direction that in the actual direction of c. Let's do another example just to really make that clear. Here's a and b again. So we know we need to be I've drawn these lying in a plane, so I'm now trying to draw a line that's perpendicular to that plane. Vector c must lie in one direction or the other along this line. What do? We draw on the angle. We now take our right hand and we imagine gripping that line we've just drawn in such a way that our fingers curl in the direction in which the angle is increasing. So it's like the anti-clockwise direction in this picture, and then our thumb points in the correct direction for that vector. So it's in fact these are the two opposite cases. So that's the rule. That allows you to construct the correct direction for your vector geometrically. Okay, then let's just finally wrap up by thinking about the cross product and asking whether it has those properties that we looked at before for vector addition, the commutative property. So for example, is A cross B equal to B cross A? It is not. It is not equal to it. Unlike the dot product, unlike addition, this one, the cross product, it matters the order, and in fact it simply introduces a minus sign if you swap the order of A and B. So it's not commutative. It nearly is, in the sense that it gives you something similar. It gives you the same thing up to a minus sign. It's important to remember. And you can just verify that by thinking about how we work out A and B with those diagonal products. Now, how about the associative property? Can we say that A cross B cross C, where B and C have already been worked out, is the same as A cross B and then cross C? What do we think? Is that going to work or not? In fact, this is the associative property. We might ask whether this is true, and the answer is no. Again, the cross product does not have this property, so the order in which you do your cross product, if you have doing the cross product of three vectors, does matter. We can easily convince ourselves of this just by looking at a particularly convenient example. Let's just use Cartesian vectors ijk. So let's just remind ourselves where these guys lie. They're perpendicular to each other. I, j, and k just are unit vectors going in the x, y, and z direction. So suppose we have this guy I cross k. If we try evaluating it this way round, with the I cross k being worked out first, well, that's just going to give us, in fact, minus j, which you can confirm with the right-hand rule that we just introduced. And then that, in turn, will give us k. That's fine. So we've worked out, in that instance, the answer is minus k. Now let's do it the other way round. I cross I, if we do that first, that's just going to be 0 because I cross I is 0, so it's game over already at that point. So we can see two radically different answers here, just depending on our order. Finally, we could ask about the distributive property. So are we allowed to multiply through using the cross product if the second object in our cross product is a sum of two vectors? Can we do this? Well, this at last is something that we are going to be allowed to do. It is the distributive property, and the cross product operation, the vector product, does have this property. We are allowed to do that, but of course we must make sure to keep the order the same. Okay, so I think that's everything for this video. Okay, in this lecture we're going to be looking at something called the scalar triple product. So what we're dealing with here is taking three vectors and combining them in a certain way in order to yield a single one scalar quantity. So three vectors into one scalar triple product. Suppose we have A, we dot it with B, which itself is crossed with C. That is the scalar triple product, that combination. Now here I've put brackets to emphasize to do the cross product first. But we can just write A dot B cross C without the brackets. Why? Because we have to do it in the correct order. If we try to do A dot B first and then cross that with C, it's a nonsense because that will be a scalar cross-producted with a vector. Doesn't make sense. Alright then, so let's do one. We'll make up some vectors. Let's have A is equal to 3, 1, minus 1. And B is equal to 2, 0, 4, and C is equal to minus 1, minus 2, 3. Okay, there are our vectors, and let's go ahead and work it out. So first we'll need to do the cross product B cross C. So let's write that out. So I'm bringing these down now. Remember, you can work out the cross product by whatever your favorite method is. I'm just going to do it in the method I introduced before, which is we ignore the first elements and we do the falling diagonal, here 0, and subtract the rising diagonal, -8. That gives us the first element of 8. Then we ignore the middle elements and we do the rising diagonal, gives us -4. Subtract the falling diagonal, which is 6. So that's going to give us a -10 entry. And then we ignore the third elements and we do the falling diagonal, gives us a -4, and subtract 0. So that's going to be -4. That is our candidate for our cross product, but it's always good to test. How do we test a cross product? We try dotting it with either of the input vectors and check we get 0. So here we'll get 8 2s are 16 and 4 minus 4 is -16. Add it up, that is 0. And now we try the other combination. Here we're going to have -1 on 8's -8, and then +20, and then -12. That does indeed add up to 0. It's passed our checks. Those were just checks, but it was good to do them. And so we're now very happy that that is the correct cross product. To finish the scalar triple product, we now just need to dot that with A. So let's write it out again. -10, -4, and do the dot product. That's 24 -10 plus 4 is going to be 18. That's the answer. That's our scalar triple product. It could have been a positive number, a negative number, it could have been 0. In this case, it's 18. Now, let's do another one, so I'll erase this, but we'll simply use the same 3 vectors, but we'll do them in a different order as our second example. So let's do B dotted with C cross A. So, of course, we have to start by doing that C cross A combination first. So let me write that down quickly. -1, -2, 3, crossed with 3, 1, -1. So we start with the falling diagonal, that's going to be 2, and then we subtract 3, that's -1. And then we have a rising diagonal, that's going to be 9, and subtract 1, that's 8. And then we have a falling diagonal, -1, and subtract -6, so that's going to be 5 in all. Okay, did I get that cross product correct or not? Do the dot product test. -3, there's a dot product test. -3, 8, -5, that one's passed. Let's try this dot product combination as a second check. Double check. 1 -16 plus 15. That's also going to come out at 0. So it's passed both of my checks. That one is 0 as well. We're happy that this is indeed the cross product C cross A. We now need to complete it. So what we're doing is B, which was 204, dotted with what we found, cross product -185. So we go ahead and evaluate this, -2, 0, and 20, 18 again. All right. So our second example has also given us 18. Does this mean that it doesn't matter in which order we do the elements of the scalar triple product? Let me just write down the answer to that, and then we'll look at it. It turns out that for any vectors A, B, and C, then A dot B cross C is equal to B dot C cross A. These were the two cases we looked at, and it's also equal, in fact, to C dot A cross B. This will always be true. In this case, it was equal to 18. But these three things will always be equal. There are 3 other combinations we could write down in principle. There are 3 other ways to combine A, B, and C. We could have A dot C cross B, or we could have B dot A cross C, or we could have C dot B cross A. Now it turns out that those things are easy to see what they will be, because let's just look at the difference from the ones above. I've just swapped the order of the cross product, and we know that when we swap the order of a cross product, we introduce a minus sign. So if the top 3 cases were equal to 18, the bottom 3 cases must be equal to each other and equal to -18. And in general, this is the same rule for all scalar triple products. 3 of them are equal, and 3 of them are equal to one another, but equal to the minus of the first 3, so to speak. And how can you tell which ones are equal? It's helpful to write out this little cycle, A, B, and C, written in a circle like this. if we are going around in a clockwise direction, here B dot C cross A, but that's clockwise around our wheel, then, and here's another one that's clockwise, C dot A cross B, those guys all belong together. So the guys that are in the clockwise direction all belong together, and the anti-clockwise guys, they belong together, and they're the minus of one another, these two groups. All right, so that's I think all we need to do as practice for doing the scalar triple product and knowing what we ought to get. Let's think about something else. I'm going to introduce you to something called the parallelepiped. That's the way I say it. I'm not sure how to pronounce it. Parallelepiped. Anyway, this guy is a three-dimensional shape. But first, I'm going to remind you of what a parallelogram looks like. So here's a rectangle, and here's a parallelogram that we get if we have the pairs of the sides are parallel to each other, but they are not at right angles around the vertex. Now consider this rectangular box, and let's tidy it up. There we are. And consider what happens if we build it out of edges that are in groups of parallel edges, but are not all at right angles to each other. So let's see if I can draw this reasonably realistically as a three-dimensional object. So I'm going to draw this, and then I'm going to stress which edges are parallel to each other. Alright, here we are. Okay, let me change color. So consider these four edges of the object are all parallel to each other in exactly the same way that in our simple parallelogram these opposing edges were parallel. And then these four edges are all parallel to one another again in our 3D shape, just as these two edges are parallel. And then we have another set. These four edges here in yellow are also going to be parallel to one another. That object is a particular three-dimensional solid. It's clearly a generalization of the box, in that we're allowing ourselves to have slanting edges if we want to. Now let's introduce three vectors, A, B, and C, to represent these three kinds of edges. You see that all the green edges are the same vector A, and so on. What happens if we do A dot B cross C? That, it turns out, the magnitude of that, if we drop the sign then, the magnitude is just the volume of this shape. So it contains, of course, the simple case of a rectangular box as a special case, but this will work for any parallelepiped that we care to think of. The three vectors can always be combined with the scalar triple product to give us the volume. And that's the end of the video. Welcome to the third topic in this video series, where I'll be introducing the matrix and thinking about what is a matrix product. Alright, so essentially a matrix is nothing more than a grid of numbers. Simply a grid of numbers that could be positive or negative or fractional or zeros. And when we specify the shape of our grid of numbers, we do so simply by stating how many rows we have and how many columns. So we're going to hear about rows and columns a lot in this video. In this video course, I'm going to use a particular way of writing a matrix as a symbol. When I need to do that, I'm going to just use a capital letter, and the letter is going to be double underlined. I'll double underline that symbol. So here we go, A underline, underline. That means the matrix A. And how would we write it? So let's, just like this, essentially a grid of numbers, and we put it in curvy brackets just to give it some structure. So this is 3 rows, 2 columns, that one. Here's a matrix B. Let's make it a square matrix. Let's put in a fraction to show we can. -10, 0. Okay, so there are 2 different examples of a matrix. Easy enough, but it gets more interesting when we try and combine them. So I want to talk about matrix multiplication. Addition is simple, and it's just element by element addition, but multiplication is not so simple. So here's how we write it. The multiplication of matrix A by matrix B is simply written like this, AB, and it gives us some new matrix C, which may be a different shape from both A and B, as we'll see. Let's give ourselves a couple of examples. 3, 0, minus 1, 2, 3, 4, and matrix B can be just 1, 2, 0, minus 3. So there are our two matrices. Here I've chosen them such that AB, that multiplication, will work. It will exist. But actually, if we try it the other way round, it will turn out that the multiple of those two matrices doesn't even exist. It's not a well-defined thing. So this is an extreme case of an operation not being reversible in its order. In other words, matrix multiplication is not commutative. Okay. So let's just erase that and go ahead and see how the multiplication actually works. The trick is to multiply each row of matrix A, the first matrix, by each entire column of matrix B. What does that mean? Well, let's write out our example. 3, 2, 0, 3, minus 4, minus 1, minus 1, 4, 1, 0, 2, minus 3. Now I know that this guy is going to have 3 rows and 2 columns, the output matrix. You'll see why in a bit. I'll just put these blanks in for now. The question is how to work out each of these numbers. Let's choose this one first. Okay. Now notice this guy's address, if you like, is row 1, column 1 of the output matrix C. I'm going to need to, in order to work this guy out, I'll need to look at the whole of row 1 in the first matrix, in matrix A, and the whole of column 1 in the matrix B. I'll need to combine those guys. And how do I combine them? I just multiply element by element as I go along the row and down the column. So 3 times 1 just gives me 3, and then I add on the next combination. 2 times 2 is 4, so 3 plus 4 is going to give me 7. That's how I combine those two. I'll jump back here and I'll erase there, and I'll just put in my 7. Alright, so that's the general way it works. Let's go ahead and do the other elements of our matrix C. Let's do this one. Notice this is still row 1, so I want that first row. It's now column 2, that's its address, so I want the second column. 3 times 0 and 2 times minus 3 is how I'll work that out, and that's just going to be minus 6. So let me jump backwards and erase my blank symbol and write in minus 6. Okay, maybe I went a bit fast. Let me spell this one out more explicitly. Okay, so here I now have row 2, column 1. That's the address of that guy. I want all of row 2 and all of column 1. I want to look at those guys and I want to multiply along. So 0 times 1 and 3 times 2. That's going to give us just 6 in total when we add them up. So let me erase and put in 6. And now this element, that's row 2, column 2. So I want all of row 2, I want all of column 2. I multiply 0 times 0, and 3 times minus 3 is minus 9, so that's going to be a minus 9 if I go backwards and just put in minus 9 here. Now we're finally on to the final third row, so we're going to want the third row of A, and in this case the first column. So that's 1 times minus 1, and 4 times 2 is 8. That's going to be 7, minus 1 plus 8, and then finally last row, last column, 4 times minus 3 is 12, and a 0, minus 12. Alright, so there we are. That is our matrix product C, formed by combining each row and each column. It's quite a lot of work, and it would be even more if we had bigger matrices. But we said that we get something quite different if we try multiplying A and B in the other order. So let's go ahead and do that now. What if we have 1, 0, 2, minus 3, that's B, onto 3, 2, 0, 3, minus 1, 4, that's A. So we can try it. We try it and multiply row 1 by column 1, and we immediately find we cannot, because they are a different length, a different list. So there is no third element of our row to multiply with our third element of the column. Just pause the video here and have a look at that and see why that must be impossible for us. And so sometimes matrix multiplication is impossible. Alright, let's look at a few little further examples, and you may want to pause the video to convince yourself in each case it's true. Is this thing possible, for example? Pause it and think. This one is not possible. This is not possible, again, because there are two elements in, say, the first row of A and three elements in the column, single column of B. There's no way to do that as a series of element by element products. How about this? We just have this row matrix and this column matrix. Can we do that? Yes, this one is perfectly possible. Actually, it just produces a single number. In fact, it's a bit like a dot product. It's the whole of row 1 times, which is the entire matrix, and then the whole of column 1 in B. This thing is called a row matrix, and this other guy is called a column matrix for obvious reasons. Okay, how about this? Let's have a look at this one. What if I swap the order of my row and column? I just swap them around. Can I do that? Is that going to produce a legitimate matrix? Actually, yes it will. This time, swapping our two matrices A and B around has produced something which exists. It's actually a huge matrix. It's 3 by 3. It must have 3 rows and 3 columns because A has 3 rows and B has 3 columns. How does it work? Let's look at that guy, for example. It's just simply the number there, which is row 1 is just a number and column 2 is just a number, single number, so we just do that product. There's no problem. Pause the video if it's confusing. Alright, so again, the point here is that A times B is generally not equal to B times A. Even if they both exist, they may not be the same, they may not even be the same shape. However, we can go on and ask about the other kinds of properties of the matrix product operation. A onto B times C, is that the same as A times B onto C? Does the order matter? Actually, it is the same. It does work. In other words, we have the associative property. How about A into B plus C, sum of two matrices? Yes, we can have A onto B plus A onto C. That is therefore the distributive property. Matrix multiplication does satisfy those things. It's just not commutative. Okay, let me make a bit more room up here in the top of the screen and put one final puzzle up. Suppose I have this 2-row 3-column matrix and then a mystery matrix M, and then I have a simple column matrix of 2 rows, and I'm asking what shape should matrix M be, or is it possible? Pause and think about that. And in fact, it's just a column matrix of 3 elements. You may want to just meditate on that and see that it's correct. Okay, that's the end of this video.
Okay, welcome to this video. In this one, we're going to take a look at how to work out a determinant. What is it? How can you find determinants of various sizes? So a determinant is a scalar. It's just a number, could be positive, could be negative, could be 0, and it's derived from a square matrix. A single number derived from an entire matrix. Now, the determinant of M would be written with M with the modulus signs either side of it, even though it can be a negative number. So here's an example of M, and here is how we would write the determinant of M. Note that we don't bother writing squares, straight sides and curved brackets as well. There's no point in that. It's just enough to have the straight line sides. So let's start with the definition of a 2 by 2 determinant. That's the easy case to look at. So let's write out a general 2 by 2 just using symbols. We'll have A, B, C, D. Written inside our straight line sides indicates a determinant. It's simply AD minus BC. Okay, so that's the falling diagonal, the leading diagonal is also called, minus the rising diagonal, multiplied together. Very simple, and that is how you can just look at and evaluate a 2 by 2 determinant. So for our example, 1, 2, 3, 4, 1 times 4 is 4, subtract off 2 times 3 is 6, and so that's going to give us minus 2 is the determinant. Okay, so a 3 by 3 determinant is going to be a bit more work. What we do is, when we have a 3 by 3 determinant, we evaluate it by breaking it up into a number up to 3 smaller determinants, each of which is a 2 by 2, and for that we have our definition for immediate evaluation. So we break up bigger determinants into little ones and then evaluate them. Now I'm going to write out something here that's like a chessboard, but instead of black and white I have pluses and minuses. You'll see why in a moment. The thing to notice though is that we alternate plus minus along each row and each column in this 3 by 3 grid. Okay. So now let's work out a 3 by 3 determinant. Again, I will just use general symbols A, B, C, D, E, F, G, H, I. Right. Now first I have to choose a row or a column. I'm going to choose this top row for the first example. And I'm going to work along this row. And I'm going to start with the A symbol. Now I go and I look on my chart and I see that there's a plus sign in that slot of my grid. That means I put down plus A. And now what I do is I ignore the whole row and the whole column that A is in, and I look at the remaining 4 numbers and I write a little determinant just made out of those guys in the same order they appear. So EF is going to be in my main determinant there, and HI. Those are the remaining 4 guys in the same order they appear. Now, B, the next term, that has a minus sign according to my chart, so I will put in minus B and multiply it by, again, a smaller 2 by 2 determinant. The one I get if I delete the row and the column with B in it and look at the remaining guys, D, F, G, I, and I just write those guys out in the same order they appear as a small 2 by 2 determinant. Finally, there's C. C appears with a plus sign according to my chart. So I need to put down plus C, and I need to multiply by, well, we delete the row and column with C in it, and we just see the remaining determinant D, E, G, H. So I simply imagine that row and column was not there, and then that's what the determinant becomes. And then, of course, those 2 by 2 determinants, I can just write down what they are using my rule of multiplying down the diagonal and of subtracting the anti-diagonal. Okay, there we are. So that is, in general, what a 3 by 3 determinant evaluates to. But it's not the only way to do it. Let's write it out again. And this time, let's choose a column and a different one. Let's choose this column. I'm also allowed to work down this. So I would start with B as my first term, and I delete the row and column with it in, and I'd see what are the remaining terms and write them D, F, G, I. Except I've forgotten something. There's a minus sign attached to that particular entry, so that should actually have been minus B. All right, and then similarly plus E, and I delete the row and column which has E in it, and then I just make a 2 by 2 determinant from, in this case it would be the corner elements, A, C, G, I. And then finally minus H, and delete the row and column with H in it, make a 2 by 2 determinant of what's left, A, C, D, F. Okay, and of course I could then write out these 2 by 2 determinants explicitly. But the point is, it will give me the same answer. Let's do an example and see why we would choose one method or the other. So here are just some random numbers I'm making up. Let's stick that in. It's 3 by 3. First off, let's work along the top row, and as we did in our first example. So that's going to be 3. Let's put in the full determinant here, and then minus 1, and again, the determinant I get by excluding the top row and middle column, and then plus 2. That's going to be 7, 0, 5, minus 1. And I can go ahead and I can work out explicitly what this comes out at, as you can see I'm doing here. And in fact it will be 12 plus 20 minus 14, and it comes out as 18. So there we are, we've worked out a 3 by 3. But we could have done it in a different way. Let's say we went along this bottom row. That's fine. So then it will be 5. and I will be left with 1, 2, 0, 4 for my mini determinant, and then the next element along, a minus sign, and it was a minus number anyway, minus minus 1, that's going to be 3, 2, 7, 4. Let's just see how we've done that. 3, 2, 7, 4 by deleting the bottom row and middle column of that. Now what about the third element here? Well, we actually have a 0 plus 0 times some determinant. I don't even care what that is because it's been multiplied by 0. That's the beauty of it. So I've got 5 into 4 minus 0, and then we're going to have 4 3s are 12 minus 14. So that's going to give us 20 minus 2 is 18. Same answer as before. Okay, what about if we have even bigger determinants than our 3 by 3 example there? If we go bigger still, for example, a 4 by 4, we're just going to break it up into a number of 3 by 3s, and each of those would have to be broken up into 2 by 2s. Lots of work. So here we are. Here's a general 4 by 4. We are going to expand it along a row or column. Let's say we want to expand it along this row, for example, and we'll take in turn A, B, C, D. And we'll need to know what sign to use. So here's our checkerboard or our chessboard pattern of pluses and minuses. Just extend it out now to a 4 by 4. And you can see the rule here is that if the row number plus the column number is an even number, then there's going to be a plus sign. And if it's odd, it's going to be a minus sign. You can confirm that for yourself. Look at this one. It's going to be at row 2 and column 3, and that's 5. And so that's a minus. That's one way to remember it, or just draw it out. Anyway, we're going to use that rule, so we go ahead and we write plus A, and now we need to do the entire 3 by 3 determinant that we get when we delete the row and column with A in it. So we just write out that little square block that we see is quite easy to copy across. And now we're going to have minus B, and we need to delete the row and column and then transcribe across the elements that are left as a 3 by 3. Just being careful not to make any slips. And you see that we're going to continue to, so let's delete this just to be completely explicit. I'll finish the job off. So I hope it's obvious what we're doing. We're on to plus C, and now we're going to just have E, F, H, I, J, L, and M, N, P. And then finally minus D onto what we get if we delete the top row and rightmost column, which is left over then E, F, G, I, J, K, M, N, O. There we are. That's how we handle a 4 by 4. Each of these 3 by 3s would then have to be evaluated and so on. So a lot of work. And that's the end of the video.
Okay, welcome to this fifth topic, which is eigenvalues and eigenvectors. We'll introduce the problem and we'll see how to find eigenvalues. Finding eigenvectors is for the next video. So suppose that we are given a square matrix, M, just some matrix, but we are told that M multiplied by V is equal to lambda multiplied by V for some scalar, just some number, lambda, and for some column matrix, V. And a column matrix, of course, the same as a vector. I will just say vector from now on. Okay, so this scalar lambda could be positive, negative, or 0. Meanwhile, this vector V could be anything except the trivial boring case of just zeros. It's something other than that. Our challenge then is that we're going to be given a square matrix M, and we have to look for any scalar lambda and vector V that satisfies the equation. And such a scalar is called an eigenvalue, and such a vector is called an eigenvector. So in that language, M multiplied by some eigenvector gives us back that eigenvector just multiplied by a scalar, the eigenvalue. Okay, so first off, let's notice that if we are given a candidate, a possible eigenvector V to try, perhaps for a multiple choice, then it's easy to test. We'll just go ahead and try it. So here's a square matrix, a 2 by 2, 2, 4, 1, minus 1, and suppose we write down V is equal to 1 minus 1, and this is suggested as a possible eigenvector. Well then, we would just test it out to see if it matches our equation. need to try multiplying m by v. So here we go, 2, 4, 1, minus 1, and v is 1 minus 1 as a column. And so we do row times column, that's 2, and minus 4 is minus 2. And again, row and column, that's going to be 1 plus 1 is 2. And we notice we can take out minus 2 as a factor, and then it will be the vector left is 1 minus 1, but that is just v. So minus 2 is indeed a scalar that multiplies v, and we've succeeded in proving that v is our eigenvector, and our eigenvalue that goes with it is minus 2. Okay, so that's great if we're given eigenvectors to check out, but what if we're not given any eigenvectors or eigenvalues? Then we must find any possible eigenvalues for ourselves. There could be more than one, and for each we must find the corresponding eigenvector v. And in this first video we're just going to be finding those eigenvalues. Okay, so here's a little bit of quick manipulation and aside. We know that our equation is mv is equal to lambda v. I can certainly just bring it all to the left hand side and write mv minus lambda v is equal to 0, as long as I remember to write that as vector 0. But now let's do something interesting. Let's insert the identity matrix, which won't change the equation, but it will be important for the next step. mv minus lambda times the identity times v is equal to vector 0. The identity doesn't change the equation, but now I can factor out both those two matrices, the m and the minus lambda times the identity. That's a matrix. I can factor those out, and it allows me to write that line. Now, that form of the equation, it turns out this can only be solved for any interesting v, any v other than just zeros, if the following equation is true, which we can easily prove, but we're not going to prove in this video. M minus lambda times the identity, the determinant of that is equal to 0. So we're going to have plenty of time to think about that, but let me just put a green box around it, because that is the fundamental equation we're going to use. This will allow us to find all the eigenvalues that satisfy our basic eigenvalue equation. So let's do an example. It's the best thing. Let's do m as a 2, 4. This was the one we had before. 2, 4, minus 1, little square matrix. And so let's write down what this lambda times the identity is. For a 2 by 2, it's going to be lambda, 0, 0, lambda. Very simple. And so this matrix that's the difference of the two of them, 2 minus lambda, 4, 1, minus 1 minus lambda, just the difference of those two things as a determinant, is equal to 0. That's all. So there we have it. We've just subtracted lambda off down the diagonal, but now we need to solve this. So we just write out the determinant, 2 minus lambda multiplied by minus 1 minus lambda down the diagonal, minus 4, the off diagonal, is equal to 0. Alright, so we expand this out. Minus 2 lambda plus lambda squared minus 4 equals 0. Let's come over here for a bit more space, tidy that up a bit. What have we got? Lambda squared minus lambda minus 6 is equal to 0. Can we solve this? Actually, it's quite easy to factor. That's going to be lambda minus 3 into lambda plus 2 is equal to 0. So that's true if either lambda is equal to 3 or it's equal to minus 2. And those are our two eigenvalues. We found them using that equation in the square box. Let's crack on and do one with a 3 by 3 matrix M. Here we go. Matrix M is equal to, let's have minus 2, 1, 3, 1 minus 1, 0, and minus 1, 1, 2. I've worked that one out. I've checked that before and it will work for us nicely. Now, let's remember, of course, the rule from the previous screen, and we just need to apply that. So let's go ahead and write it as write our determinant out. We need to have minus 2 minus lambda, and then just 1 and minus 1, and then 1 minus 1 minus lambda, and then 1, and 3, 0, 2 minus lambda. I'm just subtracting lambdas down the diagonal, making it a determinant, setting it equal to 0. Now I'm going to work along this row because it's got a 0 in it, so that makes me like it a bit more as a determinant. The first number is going to be minus 1. Why? Because it's a 1, and let me just quickly write out our little lookup table of pluses and minuses for doing determinants. So it was a 1, and then it picked up a minus sign, and then we have the mini determinant that's made out of those 4 terms. So that's 1, 3, 1, and 2 minus lambda. Alright? And then the next term is going to be plus, and then it's going to be, the term itself is minus 1 minus lambda, and the mini determinant that we get when we exclude that row and that column is just made out of the corner terms. That's going to be minus 2 minus lambda, and 3, and 1, and 2 minus lambda. And that's it, because the 0 term gives us nothing. So it was only those 2 mini determinants. Let's write them out. Minus 1, 2 times lambda, and then 3 times 1 is 3. Let's expand that one out. And then this one has the term in front, minus of 1 plus lambda, and then we have to expand out the determinant, minus 2 minus lambda times 2 minus lambda down the lead diagonal, minus 3 is plus 3, there we are, is equal to 0. And then we just need to tidy that up. We need to clean it up a bit. That's going to be minus of minus lambda minus 1 for the first term. Let's turn that all into pluses, multiply through by the minus 1. And here we have minus, let's make that lambda plus 1, write it that way round, and then tidy up inside here, we expand it out, minus 4 plus 2 lambda minus 2 lambda plus lambda squared, and this 3 is equal to 0. We need to keep on working to tidy that a bit more. This term here is in fact going to be just, I see the lambdas cancel out, lambda squared minus 1, that's very nice, that's come down very, very neatly. So now we can really tidy that up, and we can take out a common factor of lambda plus 1, and the first term was just that, so there's 1 for that. And the second term we've just found is lambda squared minus 1. Pause the video and check you agree that that's a tidied up version of the equation. Now the way that can be 0 is either the first term is 0, which requires lambda is equal to minus 1, so there's one eigenvalue for us, that's one option. One of our eigenvalues has been found. Or the second term here has to be 0, so let's do a bit more work with that. What we're saying is, to neaten that up, we're saying that 2 minus lambda squared is equal to 0. In other words, lambda squared is equal to 2, and so lambda is going to be plus or minus square root of 2. That's 2 more eigenvalues, 3 in all, that we found for this 3 by 3 matrix. And in the next video, we'll see how to take each of these values and derive the corresponding vector. This is the second of 2 videos that looks at eigenvalues and eigenvectors. In the first video, we have seen how to find eigenvalues, and we write these as lambda. For each lambda, how do we find the eigenvector, an eigenvector that goes with it? We know that our fundamental equation that we're working with here is that when matrix M multiplies an eigenvector V, it just gives us back that V scaled by lambda. And another way to write that is that M minus lambda times the identity multiplied by V is equal to vector 0. This is the same equation written 2 different ways. What we need to know now that we have obtained our lambda values, we just need to look at one of these equations and figure out an acceptable vector. I find that it's more useful to use the form on the right hand side. Okay, let's look at a particular example. We'll have the matrix 2, 4, 1, minus 1. We looked at this before and we found already that its eigenvalues are equal to 3 and minus 2. What we're going to do now is we're going to take those values one at a time and figure out an acceptable eigenvector. We're going to write our vector that we need to find as just x and y, where we need to find these x, y values. Now take a look at this green underlined equation, and in particular the matrix, which is a difference of 2 different matrices, M and lambda times the identity. Now that we have our lambda value of 3, we could write out that difference matrix. It's going to be 2 minus 3, and then just 4, and then just 1, and minus 1, minus 3. There it is. And we're saying that when that multiplies our vector xy, it gives us 0, 0. So let's go ahead and clean this equation up. We have minus 1, 4, 1 minus 4 onto x and y. If we want to be explicit about that, we can multiply out. It means minus x plus 4y and x minus 4y, and that we know is equal to 0, 0. Now what we immediately notice here is that whilst this equation between two column vectors is telling us two things, it's actually telling us the same equation twice. So we can see here that we're saying minus x plus 4y is equal to 0. We're also saying that x minus 4y is equal to 0. That's telling us the same thing. Is that a problem? No, that's exactly what we want to see at this stage. We should find that when we work on eigenvalue and eigenvector problems based on a 2x2 matrix, then really only one of these rows in the final expression constrains us, and the other one doesn't add any new constraint. So this is exactly what we want. So now, how do we go ahead and solve it? We're saying that minus x plus 4y is equal to 0. Of course, we can just rearrange this to say instead that 4y is equal to x. And that's the only constraint we have. What we're allowed to do is we can choose the simplest values of x and y that will make this work. So I'm going to choose y is equal to 1, and then I'll find that x is equal to 4. And that is a perfectly acceptable eigenvector, 4, 1, to go with my eigenvalue. We will always have this freedom in choosing the elements of our eigenvector. Really, this freedom simply corresponds to choosing how long the eigenvector is, in other words, its magnitude. Because if a particular eigenvector satisfies our equations, a scaled version of that same eigenvector will still satisfy with the same eigenvalue. Now, while the eigenvector can have any length, we might specifically have been asked for a normalized eigenvector. That simply means we need to take the one that we found and scale it to have unit length. So in this case, since it's 4, 1, we need to divide by root 17 to scale to unit length. Simple as that. So there we are. That's our eigenvector and a normalized version of it. Now we still haven't found the eigenvector for the other eigenvalue, which was minus 2. Let me just move this up on the screen to make space to do that at the bottom. So here we go. We do exactly the same procedure. We subtract minus 2 on the diagonal. 2 minus minus 2, and 4, and 1, minus 1, minus minus 2. Lots of minuses there. So let's tidy that up. That's going to be 4, 4, 1, and in fact another 1. And then times xy is equal to 0, 0. As before, we see that really this is the same equation twice. There's only one constraint, and we can read it off simply as x is equal to minus y. So if I choose x is equal to 1, for example, then I'm going to write down an eigenvector 1 minus 1. Or if I'd chosen y is equal to 1, then it would have been minus 1, 1. It doesn't matter, they're both correct eigenvectors to go with our eigenvalue. But if we want to normalize, we'll need to divide by the magnitude 1 over root 2. Okay, so there are acceptable eigenvectors to go with the eigenvalue minus 2. Okay, so now let's find the eigenvectors that go with our eigenvalues for our 3 by 3 matrix M, which was minus 2, 1, 3, 1, minus 1, 0, minus 1, 1, 2. We looked at that before in the previous video, and we found the eigenvalues, which were minus 1, root 2, and minus root 2. And I've put little subscripts on our lambdas here so we know which one we're dealing with. Let's deal with lambda 1 first, which is the one that has value minus 1. So
I'll write over here the little equation that we're using over and over again, which is that m minus lambda times the identity multiplied by our vector is 0. Okay, we need this difference matrix, so we subtract off the diagonal 1 minus minus 1, and then 1, 3, 1, and minus 1, minus minus 1, and 0, minus 1, 1, and 2 minus minus 1. And that's on x, y, and z, because we now need an eigenvector with 3 elements, and it's going to be equal to, we'll simplify the matrix to minus 1, 1, 3, 1, 0, 0, minus 1, 1, and that'll be a 3. And that again is on our x, y, z eigenvector is equal to 0, 0, 0. Now what we immediately notice is that, as before, we don't really have 3 different equations captured by our matrix equation, we only have 2. In fact, this is very obvious in this case because the bottom row is the same as the top row. That's not always the case. It's not always the case that the rows are actually identical, but we will always find, if we check, that there are only really 2 independent equations when we're dealing with 3 by 3 eigenvalue problems. We only have 2 equations, really. Now I'm going to highlight this row here, 1, 0, 0. That's just saying, in fact, that x is equal to 0. Now if we take either the top row or the bottom row, we have minus x plus y plus 3z is equal to 0, or y is equal to minus 3z. Okay, so now we simply choose any values of y and z. X has been dictated to us, but any values of y and z that satisfy these rules. So if I choose z is equal to 1, that's going to give me y is equal to minus 3. And I can straight away then write down a satisfactory eigenvector. It will be 0, minus 3, 1. As simple as that. It doesn't matter where the minus sign is. I could equivalently have chosen z is equal to minus 1, and then I'd have 0, 3, minus 1. If I normalize, then I'll need 1 over root 10, that being 3 squared plus 1 squared, and so that is a complete solution for our first eigenvector. We found it in simple form and in normalized form. This is the eigenvector that goes with eigenvalue minus 1. We can go ahead, however, and check this eigenvector to make sure that it works. So for that we'll simply need to write out our matrix M, the original matrix, which was minus 2, 1, 3, 1, minus 1, 0, minus 1, 1, 2. We have our vector 0, 3, minus 1. We just need to do this sum. So the first element is going to be minus 2 times 0, and then there's a 3, and I see there's a minus 3, so that does give us 0. And our second element is, the only non-zero element will be minus 3. And our third element there gives us 1. And we can write that as simply minus 1 onto 0, 3, minus 1. And so indeed, we found that this vector works with the eigenvalue of minus 1. Now we can continue to look at, to find the other eigenvectors, but first let's take a pause and review the steps involved. So we're looking at rules for solving eigenvector problems. Eigenvector problem is where we have a square matrix M, and we say that M multiplied by some special eigenvector gives us back that eigenvector times just by a value, the eigenvalue. We find the possible eigenvalues using this equation involving a determinant of a difference of 2 matrices. In general, there are going to be n solutions for an n by n matrix. So 2 solutions for a 2 by 2, 3 solutions for a 3 by 3 matrix. That's because when we write the determinant, it will have lambda to the power of n as its highest order. So for example, we have cubed to deal with when we're working out for 3 by 3 matrices. Now, having found those eigenvalues, we then, for each value, need to figure out an acceptable eigenvector. What we've noticed is that generally we only have to use n minus 1 of the rows in the equation that we're working to satisfy, and that meant just one row in the case of 2 by 2 problems, and 2 of the rows in the 3 by 3 problems. We had some freedom as to what values to choose for our eigenvector, and in fact that freedom corresponded to just scaling the entire eigenvector to a greater or smaller magnitude, and if we were asked to normalize, we would simply work it out using whatever values we like, the simplest values, and scale it at the last step so that it has unit length.
Okay, so we've covered a lot of ground for one video, and this would be a good place to just stop watching if you like. But I would like to carry on and solve the remaining 2 eigenvectors for our 3 by 3 example. Because they involve a square root 2, they're actually a bit more messy and tricky to do, and in a way I think that makes for a good, interesting example to see. So let me go ahead and cut back to the screen that we had before with our matrix M spelt out and our possible eigenvalues, and we'll now take the value lambda subscript 2, which is square root 2. So then, as usual, we need to subtract that down the diagonal, so we'll have minus 2 minus square root 2, 1, 3, 1, minus 1 minus square root 2, 0, minus 1, 1, 2 minus square root 2. And that is the thing which, when multiplied by our unknown eigenvector xyz, should give us 0, 0, 0. Now, one thing we notice here is the rows look all different. It looks like we've got 3 different equations captured in this matrix equation, but they are not. If we examine them carefully enough, we'd find that we could generate one of these rows from the other 2. And in fact, we're only therefore going to need to use 2 of them. You could pause the video and play with it and see if you can show this, but it must always be the case unless we've made a slip earlier. Okay, so I see that the middle row has a 0, so I'm going to start with that one. It says x plus minus 2 minus root 2 times y is equal to 0. And that means that if I choose a simple value for y of 1, then I can immediately say that x moving across is going to be 1 plus root 2. Good. So now I'll use the top line, which is minus 2 minus root 2 x plus y plus 3z is equal to 0. And I'll substitute in the values that I've already picked and inferred. So I'm going to get 1 plus root 2 onto minus 2 minus root 2, that's the x term, plus the y is 1, plus 3z yet to be found is equal to 0. Rearrange. So put z on one side, divided by a third, expand this thing out, minus 2 minus root 2 minus 2 root 2 minus 2 plus 1. Alright, oh, and there's a minus sign because we've moved it all to the other side from the z, of course. Now we need to tidy this up, but what I notice is that inside the brackets I have a minus 3 and a minus 3 root 2, and that will cancel with a factor of a minus in third at front, and just give us a very simple expression of 1 plus root 2. So that's our z term. Okay, we've found a compatible set of x, y, and z values, so we can now write down an acceptable eigenvector. 1 plus root 2, 1, 1 plus root 2. There we are. That is an acceptable eigenvector, and here's where we found those numbers, that goes with the eigenvalue lambda 2 is equal to square root 2. Note that I used the same subscript 2 on my vector so that I make it clear that lambda subscript 2 goes along with vector subscript 2. So now our only remaining task is to look at the third eigenvalue, which was negative root 2, and find a compatible eigenvector for that one. So as always, what we need to do is take the vector m and subtract the lambda value we found off down the diagonal. And because we're subtracting a minus number, we can just add it instead, of course. So that will be minus 2 plus root 2, and then 1, and then 3, and then 1, and minus 1 plus root 2, and 0, and minus 1, and 1, and 2 plus root 2. And that matrix, when multiplied by our unknown eigenvector xyz, will give us 0, 0, 0. Now, as before, our middle row looks nicest here. It's just telling us that x plus root 2 minus 1, put it that way around,
y times y is equal to 0. That means if I chose y is equal to 1, obvious choice, then x is equal to 1 minus root 2, watching for signs. Now if I take let's say the bottom row, I can have minus x plus y plus 2 plus root 2 times z is equal to 0. But I can substitute in the values I found, so that will say that square root 2 minus 1 plus 1 plus 2 plus root 2 z is equal to 0. Okay, I've got some work to do to find out the value of z here. I'll start by rearranging just to put 2 plus root 2z is equal to minus root 2 on the other side, but I still need to do a bit more work. Divide both sides. I notice I can simplify by a factor of root 2. I can write this as z is minus 1 over root 2 plus 1. Pause the video and check you agree with me. And then I'm not happy with that because I don't want to leave z as a fraction. I could do, but that would make a very messy looking eigenvector. I notice there's a trick I have up my sleeve. I know that if I multiply the top and bottom of a fraction like that by root 2 minus 1, it will simplify. I will then find that the top, of course, is 1 minus root 2, but the bottom will be 2 plus root 2 minus root 2 minus 1, and that whole expression just comes down to 1. Finally then, z is equal to 1 minus root 2. We've now found our x, y, and z values that are acceptable. So we're saying that vector 3 that goes with the lambda 3 value is 1 minus root 2, 1, 1 minus root 2. That is an acceptable eigenvector. So we're done. For our 3 by 3 matrix M, we found the 3 eigenvalues, and for each of them, an eigenvector. The last two of these, which involved the root 2, were more tricky just because there was more to keep track of, more messy expressions, but the basic maths is the same every time.